NASA crashed a spacecraft into an asteroid on purpose, and it worked better than anyone expected. Hey, so I want to tell you about something that happened on September 26th, 2022. And I think by the time this video is over, the way you think about the sky above you is going to be fundamentally different. On that day, a spacecraft called DART, the Double Asteroid Redirection Test, slammed into a small asteroid moon called Dimorphos at roughly 14,000 miles per hour. Head-on, deliberately. While over 1 million people watched live on NASA's feed, Dimorphos is about 160 meters across, roughly the length of a football field and a half. It orbits a larger asteroid called Dimorphos. The two of them circle the Sun together as a binary system. Neither one was heading for Earth. That was never the point. The point was to find out whether we could move one. Before the impact, Dimorphos completed an orbit around Didymos every 11 hours and 55 minutes. NASA expected the impact to shorten that orbit by about 10 minutes. That was the target. That was what the models predicted. That was what 4 years of mission planning said should happen. The actual result was 33 minutes, 3 times better than predicted. And the reason it worked so well is genuinely fascinating. The impact did not just push Dimorphos sideways with the force of the spacecraft. It blasted debris off the surface, chunks of rock and dust, and that debris acted like a jet, pushing the asteroid even further. The ejected material did more work than the spacecraft itself. Think about that for a moment. We did not just nudge an asteroid, we turned it into its own engine. That was the first time in the history of life on this planet that any species deliberately changed the trajectory of a celestial object. Not observed one, not predicted one, changed one. But here is the question that this video is actually about. If we can move an asteroid, what happens when we need to? How much warning do we actually have? What does the system look like? And what if the system fails? To answer that, we need to go backwards, a long way backwards, to the last time something came from above, and nobody could do anything about it. 66 million years ago, an asteroid roughly 10 kilometers across hit what is now the Yucatan Peninsula in Mexico. It was traveling at approximately 20 kilometers per second, about 44,000 miles per hour. The impact released energy equivalent to roughly 10 billion Hiroshima bombs. Not a metaphor. A calculated estimate based on the size of the crater, the Chicxulub crater, which is 180 kilometers wide and 20 kilometers deep, buried under centuries of sediment. What happened in the minutes and hours after the impact is something that new research, published as recently as July 2026, has revised significantly. And the revised version is worse than the old one. The original model went like this. The asteroid hits. Dust is thrown into the atmosphere. The dust blocks the sun. A global winter sets in. Over months, plants die, then herbivores, then the predators that depend on them. Starvation, collapse, extinction. Slow, cold, dark. The new research from Purdue University, published in the Journal of Geophysical Research, says that model understates what happened in the first hours. When the asteroid struck, it blasted molten rock into suborbital trajectories. That material circled the planet and re-entered the atmosphere. Friction heated it. The sky began to glow. Previous models showed this thermal pulse was severe, but not quite hot enough to ignite forests globally. Then in 2023, researchers found something in the rock record. A layer of ultrafine dust at the extinction boundary. Not the glass beads everyone knew about. Something finer. Rock vapor that never got the chance to condense. When they added that dust layer to the model, it changed everything. The fine dust acted as insulation, a blanket over the planet, trapping the heat and radiating it back downward. Surface conditions came out 3.5 times more intense than previous estimates. hot enough to ignite vegetation, hot enough that anything not underground or underwater had no chance of surviving. The lead researcher, Brandon Johnson, said the models now put them in the range of killing off nearly everything within the first hour or two. Not a long, dark winter. A single afternoon. Within hours of impact, most life on land was already gone. The winter that followed finished what the fire started, but the fire came first. That is the scale of what happens when something large enough hits this planet without warning. And for 180 million years, the dinosaurs had no way to see it coming and no way to stop it. The question is whether we are any different. February 15th, 2013, Chelyabinsk, Russia. About 9:20 in the morning, local time. A white streak appeared across the sky. Dashcam footage, there is a lot of dashcam footage from Russia, captured it perfectly. A blinding line of light cutting horizontally across the winter sky, brighter than the sun. About 30 seconds later, the shockwave arrived. Windows blew inward across the city. Glass shattered in buildings across a 50-mile radius. Over 1,500 people were injured, almost all of them by flying glass, not by the asteroid itself. The explosion, which happened high in the atmosphere, at about 30 kilometers altitude, released energy equivalent to roughly 500 kilotons of TNT. That is about 30 times the yield of the Hiroshima bomb. The object was a roughly 20-meter asteroid. The size of a 6-story building, it weighed roughly 12,000 tons. And it entered the atmosphere at about 19 kilometers per second, 42,000 miles per hour. Nobody saw it coming. Not NASA. Not the European Space Agency. Not Russia's own space agency. Not a single telescope, survey, or early warning system on Earth detected it before it arrived. And the reason is not incompetence. The reason is physics. The Chelyabinsk asteroid approached from the direction of the Sun. It came in on the daylit side of Earth. Every ground-based telescope is pointed at the night sky. By definition, you cannot observe stars in the daytime. And this object was small enough that no space-based instrument detected it either. It simply arrived. Unannounced. No warning. No detection. No time to react. If the same object had been just slightly larger, say 50 meters instead of 20, the outcome would have been fundamentally different. A 50-meter asteroid would have reached the ground. The airburst would not have dissipated in the atmosphere. It would have been a surface impact. The energy would have been concentrated on a single point rather than spread across a shockwave. And if it had arrived 3 hours later, just 3 hours, the Earth would have rotated enough that the entry point would have been over Western Europe instead of Siberia. That is the uncomfortable truth about asteroid impacts. The difference between a spectacular dashcam video and a catastrophe is not intelligence or preparation. It is luck. And now let me tell you about an even older event, one that was not luck at all. June 30th, 1908, Tunguska, Siberia. A remote, uninhabited region of taiga forest. An asteroid, estimated at 50 to 60 meters, entered the atmosphere and exploded at roughly 8 kilometers altitude. The airburst flattened roughly 2,150 square kilometers of forest. 80 million trees knocked flat in a radial pattern, all pointing outward from the blast center. If the Tunguska event had occurred over a major city, it would have killed millions. It did not, because in 1908 Siberia was almost entirely empty, and because once again, the entry point was determined by orbital mechanics and rotation timing, not by human planning. 2 events, both over Siberia. Both avoided catastrophe by geography rather than detection. That is not a system. That is coincidence. And coincidence is not a plan. Let us be precise about the scale of what is out there, because this is not speculation. This is accounting. As of 2026, NASA's Center for Near-Earth Object Studies has catalogued over 35,000 near-Earth objects. These are asteroids and comets whose orbits bring them within 30 million miles of Earth's path around the Sun. Of those 35,000, roughly 2,400 are classified as potentially hazardous. That designation has a specific measured definition: an object larger than 140 meters that passes within 4.65 million miles of Earth. That is about 19 times the distance to the Moon. Why 140 meters? Because that is the threshold at which an impact transitions from a local disaster to a regional catastrophe. A 140-meter asteroid hitting land would release energy equivalent to roughly 300 megatons of TNT, about 20 times the yield of the Tsar Bomba, the largest nuclear weapon ever detonated. It would flatten everything within a 50-mile radius. If it hit water, and given that the Earth is 70% ocean, water is the more likely target. The tsunami would devastate every coastline within 1,000 miles. Above a kilometer in diameter, the language changes again. A city killer becomes a civilization killer. The energy released would be sufficient to trigger global climate effects: the dust, the fires, the long winter. Chicxulub scale. And here is the number that deserves to sit with you. Of the estimated tens of thousands of near-Earth objects larger than 140 meters, less than half have been found. We have catalogued fewer than half the objects that could cause regional devastation. The other half are out there. We just have not found them yet. The known catalogue is not a complete list of threats. It is a partial inventory. And the gaps in that inventory are not academic. They are the spaces where an undetected asteroid could be right now, on an orbit we have not computed, approaching from an angle we have not surveyed, at a speed we will not be able to respond to without warning time we may not have. That is not a reason to panic. It is a reason to finish the inventory. The good news is that the inventory is growing. Every year, thousands of new near-Earth objects are discovered, tracked, and their orbits computed with increasing precision. The system that does this is not one telescope. It is a network, spread across multiple continents, operated by multiple agencies, funded by multiple governments. NASA's primary workhorse surveys are the Catalina Sky Survey in Arizona, Pan-STARRS in Hawaii, and ATLAS, the Asteroid Terrestrial Impact Last Alert System, with stations in Hawaii, Chile, South Africa, and the Canary Islands. ATLAS is specifically designed for last resort detection, finding objects in the final days or weeks before a potential impact, when more time is not available. Each of these systems photographs the same patch of sky multiple times over the course of a night. Software compares the images frame by frame. Anything that has moved between exposures is flagged, because anything that has moved is, by definition, close. And close means it could be relevant. Once an object is flagged, its position is measured, its brightness is recorded, and its approximate orbit is computed. That orbit is then compared against the Earth's orbit for the next century or more. If the two orbits come close, within a defined threshold, the object is flagged again, this time for priority observation. More observations tighten the orbit. A tighter orbit means a more precise prediction. And more precision means the probability of impact either climbs, in which case the alert level rises, or it drops towards zero, which is what happens in the vast majority of cases. The system works. It has found over 35,000 objects. It tracks them continuously. It computes their trajectories. And for every object currently in the catalogue, the probability of impact within the next century is either zero or so close to zero that it rounds down. But the system has a structural limitation. And it is the same one that let Chelyabinsk through. Every ground-based telescope on Earth shares the same fundamental constraint. They can only observe the night sky. That sounds obvious. but the implication is serious. An asteroid approaching Earth from the general direction of the Sun, from the day side, is invisible to every survey telescope on the ground. The sky is too bright. The glare overwhelms the signal. The asteroid is there, it is approaching, and nobody can see it. That is exactly what happened with Chelyabinsk. And it is not an edge case. Roughly half the sky at any given time is on the sunward side. NASA's answer to this blind spot is called NEO Surveyor. It is a dedicated space telescope, not on the ground, but in orbit, positioned at the L1 Lagrange point between Earth and the Sun. From that vantage point, it can look outward from the Sun's vicinity and detect asteroids by their infrared heat signature rather than by reflected, visible light. Asteroids are warmed by the Sun. They radiate that heat as infrared radiation. An infrared telescope does not need the asteroid to be lit from behind. It sees the asteroid's own warmth against the cold background of space. This works during the day. It works when the asteroid is in front of the Sun. It works in exactly the conditions where ground-based telescopes fail. NEO Surveyor is scheduled to launch in 2028. Once operational, it is expected to find approximately 2/3 of all near-Earth objects larger than 140 meters within its first 5 years. That would effectively close the detection gap that currently leaves half the hazardous population unaccounted for. But until 2028, the gap remains, and every asteroid that approaches from the sunward direction arrives without advance notice. The question, and it is a real one, is whether anything dangerous is on its way right now, from an angle we cannot survey, on a timeline we cannot extend. The honest answer is, we do not know. That is not a comfortable answer, but it is the accurate one. Now, there is one asteroid you should know about by name, because it is coming, and we can see it. Its designation is 99942 Apophis. It was named after the Egyptian god of chaos, the serpent who embodies destruction and darkness. Apophis was discovered on June 19, 2004. It is roughly 335 meters wide, slightly taller than the Eiffel Tower, peanut-shaped, roughly 27 billion kilograms of rock. When it was first discovered, early orbital calculations gave it a 2.7% chance of hitting Earth in 2029. 2.7% does not sound like much. But for an asteroid that size, an object that would release energy equivalent to roughly 1,200 megatons of TNT, about 80 times the Tsar Bomba, even a small probability was enough to trigger a full-scale alert. For a brief period, Apophis held the highest threat rating ever assigned to a newly discovered asteroid. Subsequent observations refined the orbit. The 2029 impact probability dropped to 0. The 2036 window was ruled out. The 2068 window was ruled out. Apophis is not going to hit Earth for at least the next century. But here is what it is going to do. On April 13th, 2029, a Friday, if you are the type to notice that, Apophis will pass within 32,000 kilometers of Earth's surface. To put that in perspective, the Moon is 384,000 kilometers away. Weather satellites in geosynchronous orbit sit at about 36,000 kilometers. Apophis will pass closer than your weather satellite, closer than most commercial communication satellites. It will be visible to the naked eye. If you are in the Eastern Hemisphere, Europe, Africa, Asia, Australia, and you look up at the right time, you will see a small white dot crossing the sky. That dot is a 335-meter asteroid passing close enough that Earth's gravity will measurably bend its orbit. Billions of people will be able to see it. No telescope needed, no binoculars, just eyes, and 2 spacecraft will be waiting for it. NASA has redirected OSIRIS-REx, the spacecraft that successfully collected and returned a sample from asteroid Bennu in 2023, toward Apophis. Renamed OSIRIS-APEX, it will arrive and study the asteroid during and after the close flyby. It will measure whether Earth's gravity physically changes the asteroid, whether tidal forces crack the surface, shift boulders, or trigger landslides. Separately, the European Space Agency is sending Ramses, the Rapid Apophis mission for space safety. Ramses will rendezvous with Apophis in February 2029, 2 months before the flyby, and accompany it through the close approach, recording everything. 2 spacecraft, 2 agencies. Watching an asteroid named after the god of chaos pass closer to Earth than any object of that size has ever been observed to pass. In less than 3 years. Apophis is not a threat, but it is a test. A natural experiment in planetary defense, delivered by orbital mechanics on a schedule we did not choose. And we are preparing for it. NASA's Planetary Defense Coordination Office, and yes, that is a real office with a real budget and real people who go to work every day thinking about this, has a hierarchy of responses. The response depends entirely on one variable: time. If we find an asteroid on a collision course with decades of warning, the answer is a kinetic impactor, a bigger version of DART. Hit it early enough and a tiny change in velocity, centimeters per second, compounds over years of orbital mechanics into a missed distance of thousands of kilometers. DART proved this works. The physics is no longer theoretical. If we have years but not decades and the asteroid is too large or too dense for a single kinetic impact, the concept is a gravity tractor. A spacecraft parks itself near the asteroid and uses the mutual gravitational attraction between the 2 objects to slowly, very slowly, tug the asteroid off course. This has never been tested. It is theoretically sound but remains an engineering concept on paper. If we have months rather than years, the options narrow sharply. A nuclear device detonated near the surface of the asteroid, not on it, near it, would vaporize a layer of surface material. The expanding gas acts as a rocket, pushing the asteroid sideways. This is not the Hollywood approach. You do not blow the asteroid apart. Blowing it apart creates fragments, and fragments are worse than a single object because they spread the impact zone unpredictably. Instead, you irradiate one side and let the physics of expanding gas do the pushing. No mission has ever tested this. International treaties restrict the deployment of nuclear weapons in space, although the treaties were written with warfare in mind, not planetary defense. And there is no consensus on whether a defensive use would be prohibited. And if we have weeks or days, if an asteroid is found on final approach with minimal warning, there is no deflection option. The only response is civil defense. Evacuation of the predicted impact zone, sheltering in place for the surrounding region, accepting the hit and limiting casualties. That last scenario is the one that keeps planetary defense scientists awake, because it is the one that depends entirely on detection. And detection, right now, has a hole in it the size of half the sky. DART hit the asteroid, but it left before examining what it did. The European Space Agency's Hera mission launched in October 2024. It is on its way to the Dimorphos system right now and is scheduled to arrive in late 2026 or early 2027. It is carrying 2 CubeSats, Milani and Juventus, and a suite of instruments designed to do what DART could not. Measure the mass of Dimorphos directly, map the crater left by the impact, study the internal structure of both asteroids using radar, and determine, with precision, exactly how much momentum was transferred from the spacecraft to the asteroid. This matters because DART exceeded expectations by a factor of 3. And when something works 3 times better than your model predicted, the model is wrong in a direction you need to understand. The ejected debris, the material blasted off the surface that acted like a jet, was responsible for most of the orbital change, not the spacecraft, the debris. But how much debris was ejected? What was it made of? How deep did the crater go? Would a different asteroid, made of different material, with a different internal structure, respond the same way? Or would the debris effect be weaker, or stronger, or non-existent? These are not academic questions. The next time we need to deflect an asteroid, We will not be running an experiment. We will be running a mission, and the margin for error will be 0. Hera will provide the data that turns a single successful experiment into a predictive model. A model that says, for an asteroid of this size, this density and this composition, you need to hit it with this much force, at this angle, this many years in advance, to move it by this much. That model does not exist yet. It cannot exist until Hera completes its survey. And until it does, our ability to deflect an asteroid remains demonstrated but not calibrated. We have proven we can push. We do not yet know how hard. And then there is the telescope that changes everything about detection. The Vera Rubin Observatory in Chile began operations in 2025. On a single night in February 2026, it issued 800,000 alerts to astronomers worldwide. In its first 10 hours of surveying, it discovered over 2,100 previously unknown asteroids, including 7 near-Earth objects. For context, all other observatories on Earth combined discover roughly 20,000 new asteroids per year. Rubin is expected to find millions in its first 2 years of operation. The camera at the heart of Rubin is 3.2 gigapixels, the largest digital camera ever built for astronomical use. It photographs the entire visible southern sky every 3 nights. Every object that moves between exposures is flagged automatically. The data pipeline is designed to handle up to 7 million alerts per night, once fully operational. What this means for planetary defense is direct. The catalogue of known near-Earth objects is about to grow by an order of magnitude. Objects that were too small, too faint, or too poorly positioned to be found by existing surveys will be found by Rubin. And finding them is the entire game. Every deflection technique, kinetic impactor, gravity tractor, nuclear standoff, requires lead time. Years of it. You cannot deflect what you cannot see. And you cannot compute an orbit you have not measured. Rubin does not deflect anything, but it closes the detection gap that makes deflection possible. And the difference between a detected asteroid and an undetected one is the difference between a mission and a disaster. Let me walk you through what actually happens if the system works, because understanding the process is more useful than fearing the outcome. Step 1. A survey telescope, Rubin, Atlas, or Pan-STARRS, flags a moving object. Software computes a preliminary orbit. The object is logged in the Minor Planet Center's database. This happens thousands of times a year. Step 2. The preliminary orbit intersects Earth's orbit within a defined threshold. The object is escalated for priority observation. Additional telescopes are notified. Over the following nights and weeks, more observations tighten the orbital solution. Step 3. The refined orbit shows a non-trivial impact probability, say 1 in 1,000. At this point, the Planetary Defense Coordination Office activates. An interagency working group is assembled. NASA, ESA, JAXA, and other space agencies begin coordinated tracking. The Torino scale, the public-facing risk assessment scale, moves from 0 to a higher level. Step 4. If the probability continues to climb rather than falling to 0, and in almost every real case it falls to 0 because more data almost always eliminates the risk, then the conversation shifts from observation to response. What size is the object? What is the lead time? Which deflection method is appropriate? If the answer is decades, a kinetic impactor mission is designed. If the answer is years, a gravity tractor or nuclear option is evaluated. If the answer is months, the conversation becomes political. Who authorizes a nuclear device in space, and under what international framework? Step 5. If the lead time is too short for deflection, weeks or days, the response is civil defense. impact zone prediction, evacuation, sheltering, emergency response pre-positioning, international coordination through the United Nations Committee on the Peaceful Uses of Outer Space. This chain of events is not hypothetical. It exists as a documented, exercised, interagency procedure. NASA runs tabletop simulations every 2 years. Scenario exercises where planetary scientists, government officials, and emergency managers practice the response. The most recent exercises have revealed exactly what you would expect. The system works when detection is early, and the system fails when detection is late. Everything depends on time, and time depends on telescopes. Here is where we actually stand. As of August 2026, we have proven, not theorized, proven, that a spacecraft can change the orbit of an asteroid. DART did it in September 2022. The data is published in Nature. The orbital change was 3 times larger than predicted. The physics works. We have a forensic follow-up mission on its way to the impact site right now. Hera will arrive within months and turn one experiment into a predictive model. We have 2 spacecraft heading to the most famous asteroid in planetary defense, Apophis, to study what happens when a 335-meter object passes closer than our own satellites. 1 NASA, 1 ESA, arriving 2029. We have the most powerful asteroid detection system ever built coming online right now. Vera Rubin is finding thousands of objects that were invisible a year ago. And NEO Surveyor launches in 2028 to close the one gap that ground-based telescopes cannot cover. The dinosaurs had no space program. They had no telescopes. They had no way to see it coming and no way to stop it. They were the dominant form of life on this planet for 180 million years, and they ended in an afternoon. We have had telescopes for 4 centuries. We have had the ability to detect near-Earth objects for about 3 decades. We tested our first deflection mission 4 years ago. For the first time in the 4.5 billion year history of this planet, the dominant species has the ability to see a threat coming and do something about it. Whether we maintain that ability, whether we fund the telescopes, build the missions, close the blind spots, and keep the infrastructure running, is not a question of physics. The physics is settled. DART settled it. It is a question of attention. And attention is something that fades the moment the sky looks safe. The sky always looks safe. That is the whole problem. Follow MindSnap. Facts that change how you see everything.